So in this video, we're going to look at rope pulling masses and those masses combined. So let's just quickly talk about tension. So tension is a force that's found in a rope. So we represent it as T, and it's measured in newtons, okay, because it's a force. Now, this is something that occurs in a rope when two ends are being pulled away from each other with certain forces. Now, it's important to understand that tension in a rope on one end equals the tension of the rope on the other end. If not, the rope would snap or start to tear. In Physics 20, we're going to always assume that ropes are massless and do not stretch. So let's look at a quick example here on how to deal with our forces that have to do here. And we're going to figure out the acceleration in this. So two blocks are tied together with a string as shown in the diagram. If a force of 20 newtons is applied to the 2 kilogram block as shown, A, what is the acceleration of the blocks if the surface is frictionless? So here we have an applied force. So this will be F applied. Okay, and that equals, as it stated, 20 newtons. Now, what is the acceleration of the blocks if the surface is frictionless? Now, something to understand, like let's imagine we're the ones pulling this with a rope. Okay, so we're pulling on it that way to the right. We're not just pulling the 2 kilogram object, we're also pulling the 3 kilogram object. So in reality, we can imagine this for this question as if this is a 5 kilogram object, because 3 plus 2 equals 5. Because we're taking that whole object with us. So here, this is our F applied, and that's the only force acting there. So this will be our net force. So this is our net force, and if we create our F net equation, it just equals the applied force. If we had just you don't have to write this down, but if we had some friction counteracting that, the force of friction, we would have to subtract the force of friction here. But that is for a later unit. So we don't have to worry about that. This is the only force acting on our box. Now, what is F net always equal to? Mass times acceleration. And this is where it becomes useful, because our mass here, remember, it's not just the 2 kilogram box, it's also the 3 kilogram box, because it's the whole system moving together. So this will be the masses added up together, 3 kilograms plus 2 kilograms times the acceleration. And what was the applied force? It was 20 newtons. So from here, we can solve. This will be 5 kilograms times our acceleration equaling 20 newtons. And now it's a matter of just dividing 5 kilograms. So my acceleration will end up being 4 meters per second, and we'll put it in proper sig digs. This needs to be in 2 sig digs, so 4.0 meters per second squared. And now you might be wondering what the direction is. You can either use your picture, so it'd be going right, but understand that it's in the same direction as your force. Same direction as net force. That's where they get their directions from. So hopefully that was pretty simple. Hopefully you've seen a few videos like this. Now let's do a little bit more of a difficult question. What is the tension in the string joining the two blocks? So let's now draw this diagram out just so we can analyze it down here. So we got our 3 kilogram, and then we got our 2 kilogram, and then we got our F applied here. Now, what is the tension in the rope joining the two blocks? So remember the things about tension. Here, we have our tension. and it is pulling away from the 3 kilogram box. On the other side, we have our tension here. And it is also pulling away. So I'm going to call this tension 1 and call this tension 2. Now, something to remember about physics 20 is tension in a rope on one end equals the tension of the rope on the other end, or else it would snap or start to tear. So if you think about it, if this tension was for some reason greater than tension 2, that means the 3 kilogram box would therefore be moving faster than the 2 kilogram box when it's being pulled, which makes absolutely no sense. So how do I solve for my tensions here? So anytime you solve for tension, you have to analyze the individual thing that the tension's attached to. So what I'm going to do here is I'm going to zoom in on 3 kilograms. So I'm going to first analyze 3 kilogram object, and then second I'll analyze the 2 kilogram object. So let's analyze the 3 kilogram object up close. Now if we analyze it up close, the only thing that's making this thing move is the tension in the rope. Because remember, we're kind of ignoring this part of the system now, and we're just focusing our attention on the 3 kilogram. So this is the only thing applying to the rope if we just analyze the 3 kilograms. So what the heck does that mean? Well, that means that your net force is being fully made up of by the tension. So net force equals tension. Now in the previous question, we determined the acceleration this thing's moving at. So here, my 3 kilogram object is moving 4 meters per second to the right. So that is our net force. So to figure out tension, we're going to do mass times acceleration, and this is the mass of my 3 kilograms times the acceleration of the 3 kilograms. So this will be 3 kilograms times 4.0 meters per second squared, and that's my tension. So this is just 12 newtons to the right. So hopefully that made sense. Remember, if we were asked this question and before A, we would have had to find the acceleration doing what we did in A. Because without the acceleration of the system, we have no way of solving this. Now let's analyze my 2 kilogram object. So if I draw out my 2 kilogram object, let's think about the forces just acting on my 2 kilogram object. I have my applied force occurring over here, which was my 20 newtons. And then I have my tension of my rope pulling it the other way. But we do know that the net force is pulling it to the right based on the question above. And remember, the acceleration of this is 4 meters per second. So now I can create a net force diagram or equation. So my net force is moving in the direction of my applied force. So my applied force is going to be positive, F applied minus tension. And now I can start solving for tension. So what I will do is I'm going to add tension. So I get my net force plus tension equals F applied. And then from here, I'm going to subtract my net force, and I will get my tension to equal my F applied, subtract my net force. And now it's a matter of plugging in the correct values. So my tension is going to be my F applied, which we know is 20 newtons from the question, minus mass times acceleration. Now remember, we zoomed in on the 2 kilograms. So that means my mass here, the net force is just talking about the 2 kilograms. So this will be 20 newtons minus 4 meters, the mass, which is 2 kilograms, times my acceleration. And remember, we know the acceleration based on part A, which was 4 meters per second squared. So the tension here will be 20 newtons. 2 times 4 is 8 newtons, which ends up being 12 newtons, and this would be to the left. So my tension over here is 12 newtons to the left. Now, what do you notice about our answers? There are the exact same value, just opposite directions, and that's what we assume in Physics 20. And that's why we assume it, because we can prove it, which is very, very neat. So remember, anytime you want to find tension in any type of question, you first need to know the acceleration of the entire system, and then you need to break up your system into parts and just focus on the individual objects moving. So if you have any questions, please let me know, but I hope that made sense and you're able to get through some questions on your own. Thanks for watching.